Good morning, students. Today we start right hand rule for direction of magnetic field. Okay, now you understand what is the magnetic field. Magnetic field means the attraction of the magnet, how much far it goes. So it is called as a magnetic field. So magnetic field not only for the magnet, also we have for the electricity, for the conducting wires while the current flows in that. So here through this we can understand so many things. Right hand rule for the direction of the magnetic field. So in the right hand, when we are showing, the thumb is on top, all the four fingers are rounding. So this is the way and this is the conductor. So this thumb will show the flow of the electricity. Okay, straight current carrying conductor. Okay, these four fingers folding will show the magnetic field. Magnetic field means this is the magnetic field. Okay, now the conductor is straight, the thumb is on top. That means this is the way current is flowing. When the current flows in the straight path, how the magnetic field will be? The magnetic field will be in the circular form. So like this. Okay, so that is the right hand rule for direction of the magnetic field. Very important this question. So the direction of the magnetic lines of force. Magnetic lines means what? So this one. So magnetic lines has the vector quantity. Vector means direction. Okay. So that this point is important. Just you underline. I will show this one. Okay. So here. So it is in the page. It is in the page 195. Okay. So here you see magnetic lines of force are a vector quantity. So vector means what? Direction. It has a some direction. So one side it goes now from north to south side. Magnetic lines of force it goes. So vector means write the point direction. So magnetic lines means what? This is the magnetic lines. Okay, these are the magnetic lines. So it has a vector quantity. That means it has the some direction. Okay, so this is the one. And the next one. So we go there. So here right hand rule means, so by a straight carrying conductor can be determined easily by the right hand rule. Imagine that you place a right hand around the conductor in such a way that the thumb points towards the direction of a current flow. Then the finger bent around the conductor will point in the direction of the line's force. Okay. So when the conductor is in the straight form, magnetic field will be in the circular forms. Okay. So this is the one. So draw a magnetic lines force produced by a linear conductor carrying electric. Linear means this one. If the conductor is in the straight path in the linear conductor, so how the magnetic lines will be? Okay. So all these so many examples we see the magnetic field in the electricity mostly. Okay. So here we see now in a conducting wire current is flowing from east to west. What could be the direction of the lines of force at a point? Vertically below the wire and at a point above that wire. Okay. So here you will understand about all this by studying. So magnetic field due to the circular current carrying conductor. So we have seen the shape of the magnetic field produced by a straight current carrying conductor. Imagine that the straight wire is now bent into a circular coil and current flows through it. What would be the shape of the magnetic field? So for example here they have this one. So this conductor they have put in a circular form. So when the conductor is in a circular form, current carrying conductor of any metal, when we keep in the circular form, so how the shape of the magnetic field will be? So here it is showed. Let us fix a circular coil on a cardboard sheet as shown in the figure 8. When a current starts flowing in the coil, sprinkle the iron fillings on the cardboard. We can observe that iron fillings get arranged in a concrete circles. Iron fillings means small iron like powder, we spread it and everything will make like a circular forms. Now you see everything is in the circular form, magnetic field. Okay, so as the distance increases, the lines appear almost straight to the large diameter. So now you see this is far from this central point, na? So this is far from this electric carrying conductor. So as the distance are increasing, the linear appear almost straight to the large diameter. So this magnetic force lines are becoming like a linear. Linear means it is becoming a straight like. So by using a right hand rule, we can observe that circular wire produces a magnetic field which has the lines of force in the same direction at every section of the circular coil, and therefore the intensity of the magnetic field gets magnified. Let us perform an activity to observe this phenomenon. So here it is all the magnetic lines, this is following the right hand rule. That means thumb is on top, electricity is flowing and the magnetic lines force are all is going in the same direction. Okay, so like this means going this way. Yes, this way, this side means coming this way. So going in the same direction. So here when we see in the right hand rule, the current is passing this way. So coming this way, round shape. Okay, it is going in the round shape, magnetic field. So here therefore the intensity of the magnified means become big. Magnetic field is becoming larger. Let us perform an activity to observe this phenomenon. Okay.
Due to a current in a circular coil. Magnetic field due to a current in a circular coil can be understood by the following activity. Take a drawing board and fix a white paper sheet over it. Make 2 holes A and B in the drawing board and pass a thick copper coil through it. Connect the ends of the copper coil to a dry cell through a switch and a variable resistance. Close the circuit and plot magnetic lines of force with the help of plotting needle. We can see that magnetic lines of force around the hole at A are in anti-clockwise direction. However, the magnetic lines of force near the center of the coil become almost parallel, and around the hole at B, the lines of force are in clockwise direction. In the above activity, the lines of force enter the coil from the side of the experimenter. So we can say that the face of the coil towards the experimenter act as south pole and the face opposite to the experimenter act as north pole. Now relate the above observation to the flow of current in the coil, and then we can say that if the current flows in the coil in clockwise direction facing the experimenter, then that face of the coil will act as south pole. If the current flows in the coil in anti-clockwise direction facing the experimenter, then that face of the coil will act as north pole.